All right, now we're going to talk about what logarithms are. We'll do our introduction to logarithms. So what do we use logarithms for? So we know that we can solve problems like 5 to the x equals 5 squared. If we can get these matching bases, we can set the exponents equal. Okay, but what if that's not the case? What if I want to know what power of 5 gets me to 10? Well, 5 to the first power is 5. 5 to the second power is 25, so it has to be somewhere in the middle, somewhere between 1 and 2. And to find that exact value, there is a process you can go through, but rather than going through this big long algorithm over and over again to get that answer, we use things called logarithms. Okay? So these are values that you can look up in a book, or your calculator can go through this algorithm and find you these values very quickly. So to answer or to solve for unknown exponents, especially when we can't get the basis to match, we want to use logarithms. Okay, so we know how to write things in exponential form. So for instance, 5 to the second power equals 25. So 5 is my base, 2 is my exponent or power, and 25 is the value it's equal to. Okay, now we can write that in something called logarithmic form. This is the same thing, but written in a different way. So for instance, here, when we write logarithms, we write a base as a subscript. So it's kind of the opposite of an exponent. Instead of being up high and smaller, it's down low and smaller. And the base of our logarithm is the base of our exponent. So here it would be log base 5. Okay, of something equals something. And I always remember my logarithm equals the exponent. And again, it equals the exponents because we use it to solve for unknown exponents. And that reminds me that the value that goes inside is 25, our remaining value there. So log base 5 of 25 equals 2. This is how we write this in log form. And kind of the question, remember when we had something like the square root of 9, right? The question this is asking us is what times itself twice as 9? And we know that's 3, right? If we're just looking for the positive answer. Or if it says what's the cube root of 27, which is also 3. This is asking us what times itself 3 times is 27. The question logarithms are asking us is 5 to what power is 25? 5 to what power is 25? And the answer is to the second power. 5 to the second power is 25. So one of the things we're going to need to do is to switch between these two forms. And there are some restrictions on these variables. We'll talk about those later on. Okay, for now, for each exponential or log equation, change to alternate form. So if they start me with an exponential, let's write it as a logarithm. So again, if we're copying here, remember the base of my logarithm is the base of our exponent. So log base 2 of something equals something, and it always equals the exponent. So 5 goes over here, and 32 goes inside. And again, this is asking me 2 to what power is 32? And if you look that up in your table, that is 2 to the 5th power. That log has a value of 5. Okay, what if we go backwards? Now they're giving me a logarithm, and we want to write it as an exponential. So again, this is the base, so that is also the base of my exponent. This is our exponent, so 5 to the negative second power equals the value from inside, 1/25. And this is a true statement. Okay, let's kind of work going backwards and forwards here. Our next one, this would be log base 4 of something equals something. Remember, the base of your logarithm is the base of your exponent. And that our logarithm always equals the exponent. So it reminds me, 64 is what goes inside. 4 to what power is 64? 4 to the third power. Let's go backwards again. Remember, this is the base of my exponent. This is my exponent, so 9 to the 1/2 power equals 3. And that makes sense. This means the square root of 9. Again, 9 to what power is 3? 9 to the 1/2 power, which means the square root. Okay, our next one. This is an important one as well. the base of my logarithm will be 6, right? The same as my exponent, of something equals something, and my log always equals the exponent. So again, this log is asking 6 to what power is 1? And if you remember your properties of exponents, anything other than 0 to the 0 power is 1. So 6 to what power is 1? 6 to the 0 power. Okay, and then this one, log base 5 of 5. This is saying 5 to what power is 5? 5 to the first power, right? But let's write it in exponential form. This is my base. This is my exponent. And that equals the 5 from inside. 5 to the first power equals 5. So this leads us into some properties. Like 5 to what power is 5? Well, anything to the first power is itself. So let's take a look at some of these properties. Okay, so in fact, just to kind of skip down here, since we just went through that problem, log base b of b. Like log base 5 of 5, b to what power is itself? B to the first power. So like log base 7 of 7, log base 5 of 5 will always equal 1. Kind of similarly, log base 10 of 10, 10 to what power is 10? 10 to the first power. And this one's actually even follows our same example here. B to what power, I'll just put a question mark there, is equal to b to the y power. Well, for these to be equal, my question mark has to equal y, right? Our bases are equal, so our exponents have to be equal. This ends up simplifying to y. And one of the things we'll also learn is a log base b and a base of b. Like if these match, they kind of cancel each other out, and we end up with the exponent there. Okay, and our last one here, b to what power is 1? We actually did do that in the previous slide. Our base to what power is 1? 0. Our exponent there is always 0. B to the 0 power. Any defined base to the 0 power is 1. Okay, next up, we're going to just write this one down. I don't think we use it quite yet, the change of base formula. But some calculators, when we evaluate them, we'll actually get to this later, so we do need the formula today. Some calculators won't let me put in log base 2. It'll only let me put in 2 different bases. Log base 10, which you can see up here. This is called the common logarithm, and it's usually written without a base. So if you see log and they don't write a base in, it's assumed to be base 10. Okay, so that's called the common log. So most calculators will do log base 10. Some of them will do log base e, which is a number we'll talk about next time, and that's actually usually written as natural log. So we will talk about that at another time. But if my calculator doesn't do log base 2, we need this formula so that we can type it in with log base 10. So we'll talk about that. Like for instance, if I have log base 2 of 5, okay, and I want to type this into a calculator that won't do log base 2, we can do the log of the top divided by log of the bottom. And the easy way to memorize this formula is 2 is the base, and you drop the base down here too. Or the base goes in the basement, but that's less fun. Okay, this fraction, if you type that into your calculator or into Desmos, whatever you're using, gives you the same answer that this does. So drop the base goes in the bottom, and now I can use base 10, which my calculator or all calculators will have that are scientific, to get my answer. Okay, let's see if we can evaluate some of these without a calculator. Again, if you remember what these are asking you, you might be able to come up with them without doing any extra work here. So example 7, log base 2 of 8. This is saying 2 to what power is 8? 2 to what power is 8? And if you know that power, then you have your answer. Now, if you're unsure, I'm going to show you how we can solve this. Let's let it equal some unknown value x that we want to solve for. We're going to change this to exponential form. So remember, the base will be 2. X is my missing exponent, and that will equal 8. Right? This is the same question we were just saying out loud. 2 to what power equals 8? Well, if you remember, we can rewrite 8 as 2 cubed. And now we have our matching bases. We can set the exponents equal, and we now know that x has to equal 3. Okay, likewise, let's try our next one. In fact, let's skip to 9 really quick. We'll come back to 8. This is saying 3 to what power is 27? And if you know the answer, you can just write it down. Or, once again, we can say equals x, and this will help us for more difficult ones, and write it in exponential form. So 3 is the base, x here is the exponent, 3 to what power equals 27. 27 we could rewrite as 3 cubed, and now we have our one matching base on each side. X has to equal 3 again. Okay, let's try 8 here. 5 to what power is 1/25? Now you might reason that if that's in the denominator, I need a negative exponent to get down there. So let's see though. Let's go ahead and go to exponential form. 5 to the x power equals 1/25. Now if we use our steps from our previous lesson, we can bring that up with a negative exponent. And then we can rewrite 25 as 5 squared. And if we do that, we get 5 to the x equals, multiplying here, 5 to the negative second. And now that we have our matching base, we can set the exponents equal, and x is -2. 5 to the negative second power, right? Negative puts me in the denominator, and 5 squared is 25. Okay, here's a few more examples. 2 to what power is 1/16? So again, we can say 2 to the x power. 2 to what power is 1/16? Bring 16 up with a negative exponent. And then rewrite 16 as 2 to the 4th power. Distribute your exponents here and multiply. We get 2 to the -4th. So therefore, x has to equal -4 once we got those matching bases. These next one would be a little tougher to maybe come up with. Here you could probably reason 2 to the 4th is 16. It's in the denominator, so it should be negative. Okay, here, 16 to what power is 4? Might be less obvious. 16 to what power is 4? Well, 16 we could rewrite as 4 squared if we're using our techniques. And 4 is technically 4 to the 1st. Distribute your exponents here. 4 to the 2x equals 4 to the 1st. And now we have that one matching base. 2x equals 1, or x is 1/2. 16 to the 1/2 power. Oh yeah, that means the square root of 16, and that would equal 4. Okay, that makes sense. 81 to what power is 3? 81 to what power is 3? Well, I might need to look that one up, but that is 3 to the 4th power. And 3 I can think of as 3 to the 1st. So distribute your exponents here. And now we've got that one matching base on each side. 4x equals 1, or x equals 1/4 dividing by 4. All right. That's it for this part, but we do have some graphing to talk about. We're going to look at graphing logarithms a little bit. Okay, so we graphed exponentials a little bit before. Okay, they look like this. Logarithmic functions are their inverses. And if you remember from the beginning of the year, inverses always reflect over y equals x. So whereas exponentials had a horizontal asymptote, logarithmic graphs have a vertical asymptote. Okay, so here's kind of our generic form when we graph a logarithm, and here's the one that allows us to manipulate it with a, h, and k. Now our vertical asymptote is going to be at x equals h. Okay, so whatever that h value is, and remember, because of the minus sign, it's the opposite of what it looks like. And our domain will be that x has to stay greater than h. We are going to stay to the right for it pretty much always in this chapter. In our range, this graph does continue up and down forever, sometimes very slowly going up, but it does continue up and down forever, so all real numbers. Okay, so here are some steps for graphing. We want to identify h and k and plot our vertical asymptote. So let's follow through this on our first example here. So note that again in this form, that h is normally inside here with x, and k is out here as being added or subtracted afterwards. So note that there's no h this time. So h is 0, but our k value out here is -2. So we do have a vertical asymptote at x equals h. X equals 0. So we'll go ahead and plot that in here. I'll use green. Okay, when x is 0, we have our vertical asymptote. Okay, next, use powers of the base to plug in for x and their exponent as y. So here's what we mean. We're going to kind of ignore h and k for right now. And we're just going to graph this as if h and k were 0. So let's just look at powers of 2. So 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. Even 2 to the 0 power is 1. And if you choose these values on the right as values for x, when we're plugging in, we're asking, let's say I plug in 2. Okay, so I'm plugging in 2 here into log base 2 of 2. 2 to what power is 2? 2 to the first power. And in fact, our exponents here are going to be the y values we get back. So when we plug in the values in green, plug in 1, say for x. I can draw, sorry. Plug in 1 for x. The answer we get back is actually 0, the exponent there. If I plug in 2 for x, we get back 1. 4 for x will give me back 2. 8 for x would give me back 3, etc. So these points are on my graph if there was no shifts. Okay, I know there were shifts. We'll adjust these, but let's graph these for now. We got 1, 0, 2, 1, 4, 2, and 8, 3. Okay. Now we do have a shift. No horizontal shift because h was 0. But k being -2 is a shift down 2. So to get to my final graph here, which we'll use black for, we're going to need to move all of our points down 2. So that was the only shift. My vertical asymptote stays right here because this is the vertical asymptote for the final graph at x equals h. And I just want to show getting closer and closer to that asymptote and go off to the right. Now it also says state the domain and range. Here my domain, remember x has to stay greater than h, which is 0. And our range is all real numbers. Okay, let's try 14. I know this might have been a little confusing, so let's try this again. First, identify h and k. Okay, in this case, h is actually +1. Remember, it's kind of the opposite of what it looks like. And k is +4. So as far as shifts, if we wanted to talk about those right now, we can. That's a shift right 1 horizontally and a shift up 4 vertically. Now our vertical asymptote will also be at x equals h at x equals 1. So we can go ahead and graph that in. X equals 1. This is where the asymptote will be for my final graph, the one that will have the shifts already done. So here's how we pick points again. We are going to pick points for this graph. Y equals log base 3 of x. We're going to start by graphing this, and then we're going to do the 2 shifts. So our base is 3. Let's write down some powers of 3. 3 to the 0 is 1. 3 to the first is 3. 3 squared is 9. 3 to the third is 27, and that's a really big value of x. So I don't think we're going to even use that. I think 9 is probably the last one we'll be able to fit in here. So again, if we plug in these values for x, we get back the exponents for y. So if we're making our table here, sorry, this is a little messy, but if we're making our table here for x, I'm going to plug in 1 for x and get back 0 for y. Plug in 3 for x, get back 1 for y. 9 for x gives me back 2. And if I plot these points, 1, 0, 3, 1, 9, 2, remember this is not the final graph, we need to do these shifts. Move them all right 1 and up 4. So right 1, up 4. Right on the edge there. Right 1, up 1, 2, 3, 4. Right 1, up 1, 2, 3, 4. Okay, so my graph is getting closer and closer to this asymptote. Then it starts curving up through these points and then continues off to the right. Something like that. It does continually go up. And again, my domain here is that x has to be greater than h, greater than 1, and our range is all real numbers. Okay, we'll do some more examples of this in class. I know this is a lot of information, so if you did have access to a printer, I will include the blank page for all of this.